So let's try to do this problem from Serway. This is Serway chapter 9, problem 77 from the 9th edition. So it's a problem involving energy and momentum. You've got two blocks. You know the masses of the blocks, 2 kilograms and 4 kilograms. And they're both released from a height of 5 meters on a frictionless track as shown. They undergo a head-on elastic collision at the bottom. And the question asks for determine the maximum heights to which M1 and M2 rise on the curved portion of the track after the collision. So this is my target, because I'm trying to find how high they go after they collide, right? Okay, so it's a bit of a complicated problem. You have some initial situation where they're falling down the ramp, reaching some speed, colliding with each other, and then going back up the ramp. Alright, so let's try to take it one thing at a time, and let's try to kind of strategize a little bit. So one thing to notice is that the initial height is the same for both. And why is that important? Because that means that at the bottom, the speed of the two masses will be the same. Because from conservation of energy, let's apply conservation of energy to, let's say, mass 1. We have delta K plus delta U is equal to 0, assuming that there's no friction or non-conservative forces acting on the block. So I've got K final minus K initial plus the change in potential energy. So let's pick, here I'll just pick y equal to 0 at the bottom of the ramp. So I'd have at the top 0 minus mgh, right? Equals to 0. The initial kinetic energy is 0. And so I've got here 1/2 m1, let's say v1 squared minus mgh is equal to 0. And this is the kind of well-known thing, the m's cancel, right? And I end up with that v1 is equal to the square root of 2gh, right? So the speed at which the thing is traveling at the bottom depends only on the initial height. And since they both start at the same height, that means that the speed of each one is the same before a collision. So that's going to be helpful for us. So let's see if we can take this a little bit further, and let me go to the next slide. So let's try to picture the problem a little bit more. Now I've got these two masses coming towards each other with the same speed head-on, but opposite directions, and they're going to collide. They collide elastically, and they'll bounce off with two different velocities which we don't know, right? But if we know those two velocities, we can then go back to what we did on the previous slide to figure out how high they go using conservation of energy. So our strategy is to first, let's try to find V1F and V2F using the physics of collisions. And then we can go back and use energy, just like we did on the previous slide. We can say that the final height, say h1f, will be v1f squared over 2g, and h2f will be v2f squared over 2g. This just comes from conservation of energy, like I had on the previous slide. If you rewrite it, v1f is the square root of 2g h1f, right? So that's our plan. So our intermediate targets are going to be to try to determine these two things, right? v1f and v2f. And then I can use energy pretty straightforwardly to find those final heights. So let's go and try and do that a little more carefully. So I've got my, let's focus on the collision now, right? Let's use conservation of momentum. Pi is equal to Pf for the whole system, right? And the whole system is going to be the two blocks together. This is my system. So initially, my momentum is going to be m1 vi minus m2 vi. There's the minus there because notice that m2 is traveling in the opposite direction as m1, right? So if the vector from m1 is m1 vi, the vector from m2 is m2 times minus vi, right? The minus means it's for the direction there. That has to be equal to m1 v1f plus m2 v2f. Now you might be worried, why don't I put in minus signs on the right-hand side? The reason is I don't know which direction they're moving. I just drew this one like this, but they might go off in the same direction or in opposite directions, we don't know. So if I'm careful with the signs, that stuff will come out just from my calculation. So all I'm doing right now is I'm just leaving it as a general v1f plus m1 v1f, m2 v2f, and then the directions will come out of the calculation. All right, so I've got two unknowns, v1f and v2f, but I've only got one equation here, right? So this is one equation that we got from conservation of momentum. I need another equation. Can't solve a system with two unknowns with only one equation, so I need one more equation. You could use conservation of energy, since this is an elastic collision. It gets a little bit messy because you have squares of velocities in that for kinetic energy. So if you've looked at the textbook, you can work the equation for momentum and the equation for kinetic energy together into a equation for 1D head-on collisions. And it's a quite useful equation. It's only true for 1D head-on collisions, so don't try to use this in more special cases. Also, sorry, it has to be elastic, right? So it's got to be head-on elastic collision, but we have that in this case, and the equation looks like this: v1i plus v2i equals plus v1f equals v2i plus v2f. So in this case, that looks like this: vi plus v1f equals minus vi plus v2f. So there's my second equation. I've got two equations, two unknowns, so I have to just solve those two equations for those two unknowns. So we'll do that on the next slide. Okay, so we have two equations for two unknowns. Go through it a little bit quickly. This should be pretty standard. We're just going to solve number 2 for v2f and substitute into 1. Those steps are pretty straightforward, so I'll just pause the narration and show you the result. So that's what you get when you do this substitution. And now let's solve this for v1f. So let me clean up the left-hand side. I've got v1f times m1 plus m2 plus 2m2 vi. And when I subtract this piece over to the right side, or sorry, over to the left side, I will have, instead of m1 minus m2, I'll have m1 minus 3m2. So this is what that looks like after you've solved for v1f. Now I need to go back and solve for v2f. and that's not too bad. So I'll show you what that looks like. So I just went up and took this equation and substituted in the formula for V1F. So it looks like this. You can simplify this a little bit by putting it over a common denominator. It looks like this. I'm going to get 3m1 minus m2 over m1 plus m2 times vi. Okay, so we have our now two velocities, v1f and v2f. So now we can finish the problem. We'll do that on the next slide. Okay, so those are the solutions for the final velocities of the two masses after the collision. And then to get to the actual target, which is the height at which they go, we need to use conservation of energy again, right? So conservation of energy says that if I know their initial speed, they're going to basically all of that initial kinetic energy, 1/2 mv squared, is going to be transformed into kinetic energy mgh, or sorry, potential energy mgh. So I get h is going to be v squared over 2g. So let's square both of these formulas. I will have v1f squared is m1 minus 3m2 over m1 plus m2 squared vi squared, right? And from there, v1 squared is going to be 2g h1f, right? Substituting in this formula here is equal to m1 minus 3m2 over m1 plus m2. Vi squared is going to be 2g times the initial height, right, hi. And the g's are going to cancel and the 2's cancel. So I get here a formula for h1f in terms of h1i. And I can do the same thing for h2. So let me do that very quickly. So there, that's what that looks like. So we have now our final two formulas for h1f and h2f. So all we have to do now is plug numbers into this, and then we've solved the problem. Okay, so there are our final formulas for h1f and h2f. Before you plug numbers in, you should ask yourself, does the formula make sense? So one thing we can check is the units. The units are obviously correct because I have kilograms over kilograms inside the parentheses, and then h and h on each side, so the units are okay. The other thing you could check is what's a case that is easy to handle. What if m1 equals to m2? Can you visualize what would happen? Well, if m1 and m2 are equal, they'll come down and they'll bounce off each other and they'll just go back up to the same height that they started at, right? So what happens in that case? We would have h1f would just be m minus 3m over 2m squared times hi, and that's minus 2m over 2m squared times hi, which is just hi. So the initial height is equal to the final height. And the same thing is true for h2f, right? I get 3m minus m over 2m hi, which is just hi. So at least this agrees with our intuition. So that if the masses are identical, they'll just go back up to the initial height. You can notice something interesting, that if one of the masses is 3 times bigger than the other, for example, if m1 is 3m2, then hf is equal to 0 for one of them. So you should try this out. you have two masses, one is 3 times bigger than the other, you release them from the same height, when they collide, one of them will completely stop and the other one will get rocketed off in the other direction. Alright, so all of that stuff is just kind of interesting, not the problem that we have. So now we just have to plug in the numbers. So I'll do that, show you the result, and I'll let you look at it. I hope you found this problem useful.